Hello, everyone, and welcome to today's webinar, Unconventional QC, Implementing Appropriate QC Design Strategies in Your Lab. I am Marie Stone of Lab Roots, and I'll be your moderator for today's event. Today's educational web seminar is presented by Lab Roots and brought to you by Technopath Clinical Diagnostics USA. To learn more, visit technopathclinicaldiagnostics.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. This webinar is educational and thus offers free continuing education credits. Please click on the continuing education window at the bottom of your screen to obtain your credits. I'd like to now welcome our speaker, Sten Westgard, Director, Client Services and Technology at Westgard Quality Control. Sten, you may now begin your presentation.
Thank you very much. Welcome to all of you. I'm glad that you can join us today. Very happy that Lab Roots and Technopath can bring us together on this occasion. The goal of today is to be unconventional. And we're going to talk about what the habits are, the common practices are in quality control, and how many of them are really detrimental. And I hope that by the end of this session, you'll start to re-examine what you are doing currently for QC and think about actually trying to design QC, not just doing the same thing that you've been doing for a long period of years. And I hope I'll be able to show you the benefits of changing how you do QC and changing your design strategy for each test. The benefits will come because we'll choose different rules, and we'll choose rules that help you minimize the false rejection and maximize the error detection. I do, of course, want to, again, give you the standard disclosure. Technopath is making this happen today. They are compensating me for my time. I also want to do a little shout out. Part of this presentation, I'll be calling out different sections of a new workbook that's available for free from Technopath, and it's about advanced applications in quality control. And not only can you get educational credit from listening to this session, if you download the workbook, you'll be able to proceed through it, and there's an exercise at the end, and you'll be able to get educational credit from the workbook. So you can double dip here on your educational credits. Now there's a more important disclosure that I'm required to make by my boss. And this is particularly important because you're only hearing my voice and not seeing me. And so some of you may be confused. You may be thinking you're actually talking to the rule father, or as I call him, the Westgard. I am only a Westgard. You're only listening to Sten Westgard, not the Westgard, which of course is James Westgard. And I've only been doing this for a quarter of a century, whereas the Westgard, the rule father, he's been doing it for more than 50 years. Another resource that's available to you and really is the flagship of the Westgard efforts is Westgardcom. We have more than 70,000 laboratory professional members. It's a free membership, and we give you access to more than 600 articles and downloads and graphing tools, all kinds of resources about quality control. So let's start with our first poll. We're going to talk about whether you have been actively managing your QC costs. So here we are. Have you, in the past 10 years, reduced your QC frequency? Have you widened the control limits you are using? Have you changed any of your QC rules? Have you consolidated your QC? That is, you're using fewer QC vials than you were in previous times. Or is your QC essentially the same setting as it was 10 years ago or 20 years ago or 30 years ago? Your QC is really going on autopilot, and we're going to let this percolate, and you can take a moment to answer the questions. One of the things we'll be doing during this session is not only are we polling you, but we're comparing with an ongoing survey that Westgard and Technopath have been conducting for the past several months to really give us a snapshot of what's going on in the whole world. And we'll let this go another few more seconds. You can see we still have people coming in, and changed QC rules seem to be leading. And I have to say that's gratifying. I am glad to hear that people are changing their QC rules. It means you are the right audience. You are being less conventional. You are embracing and modifying your QC rules. And wow, I'm glad to see we have so many participants today. I think once we hit around, all right, well, we're going to call it at this point, say this is about our plateau, and we see most of you, well, 35% of you, and that's the plurality, have changed QC rules. And now let's take a look at the current global survey that we're running, and we have more than 500 labs in more than 100 different countries. And here the finding is, not so many people have changed QC rules, less than 10%, and almost 2/3 of labs say they haven't made any changes in how they do QC. And that, of course, is a problem because there's so many changes in laboratories today. If you're not keeping your QC design up to date with your technology, you're probably over QCing, or in some cases you might be under QCing what you're doing. And let's remember that the control system has been a dynamic, it has been changing over the years. We used to have single analyte controls, now we're at multi-analyte. We used to have controls that were really only targeting one level, now we have multi-level, trying to hit medically important levels and trying to span as much as possible the analytical measurement range. We used to have very short life on our controls, and now in biochemistry, we might have several years of life. And we also see an increase in the open vial stability. That is, not only is it good on the shelf, it's good when it's open. These are all things that have changed over the years, and that means we can make other changes today. The things that we see in the future of controls is we want them to be more commutable and have fewer matrix effects. Unfortunately, that runs into the efficiency. The fewer preservatives and stabilizers we put in, that directly will reduce our shelf life, could reduce how many analytes we can put in a single control. So we will probably not get to a place where everything is purely commutable and there are no matrix effects. as long as our goal is we want things to last a long time on the shelf, we want scores of analytes in a single bottle, that will require more preservatives and more stabilizers, and might keep it less commutable. Beyond the selection and sort of the makeup of the controls, there is the QC rules themselves. And that, of course, is right in our wheelhouse at Westgard. We talk about QC. And here's our second poll, and this is going to be about your use of 2SD control limits. Do you use 2SD control limits, and how much do you use them? Are you using them on all of your tests? Are you using them on some of your tests? Are you using them not at all? They're not on any of your tests at all. And the history of the 2SD control limits goes back to the dawn of the laboratory era. Back when people were using flame photometers, when you were manually pipetting or you were pipetting by mouth, when your volume was in the dozens, your menu was your menu was equally small, 2SD limits were alive and well. That was the only way to do QC. And we see, yes, looks like a lot of people are using, on all of their tests, 2SD control limits. And we seem to have plateaued. Now we have a little over 200 people on the webinar. Welcome. Great to have you here. And we see, yes, almost 60% of labs are using 2SD control limits on all the tests. That is the conventional approach. And now we can compare ourselves to the global climate, where 56% of labs worldwide are using QC rules, the 2SD control practice, and that's half a century old. So the reason we stick with 2SD limits, it's more of a tradition than a science. And a very small percentage are not using 2SD limits at all. The thing we know about 2SD limits is if you run 2 controls, the expected false rejection rate is 9%. And if you run 3 controls, that expected false rejection rate rises to 14%. Now, if you want 1 out of 10 or more runs to be out of control, that's your choice. However, it's going to be filling your day with a lot of out of control events. 50 years ago, there weren't that many tests. The runs were small, the menu was small, so if you had 1 out of 10 runs out of control, it was something you could manage. But we have a huge volume of tests. We have a huge menu. We have more and more instruments. To have a 10% failure rate or higher on our QC process, that's really deleterious. It's consuming quite a bit of our time on waste. Because again, this is a false rejection. There's nothing wrong with the system, but the way you've chosen your limits means you're actually creating problems for yourself. Now we're going to give you this is our last live poll, and this is going to be about your Westgard rules. How many of you are using Westgard rules, and how much? Are you using them on all of your tests? Are you using them only on some of your tests? Or no, you don't use Westgard rules at all? And there should be kind of a difference that we see between the use of 2SD and the use of Westgard rules. If you recall, the Westgard rules were created as a replacement for the 2SD, as a way to improve your QC detection without increasing your false rejection. So try to find that sweet spot where you have good error detection and low false rejection. Now, it looks like we're almost plateauing here. About 200, 229, 230, and we're saying 2/3 of labs are saying they use Westgard rules on all of your tests. And that can be quite flattering. I will tell the rule father, my boss, that Westgard rules appear to be quite strongly alive and well here in the second decade of the 21st century. Now let's compare what we see around the world. 87% of labs report they are using Westgard rules, and that's split between on some tests and all tests. But if you look at all my tests, it's about exactly the same. So you can see that around 60 to 66%, not only in this audience, but around the world, are using Westgard rules. And less than 10% of labs don't use them at all. So it's a good tool. But if you're using all the Westgard rules on all your tests, that might be overkill. That might be too many Westgard rules. And we're at a stage where we need to think about when we should use Westgard rules and how many of them. And we should not just use Westgard rules as a default. We want to use Westgard rules when they are necessary, but not when they're unnecessary. And of course, then the question arises, well, how do you know when you need Westgard rules? That's going to bring us to the next stage where we talk about Six Sigma and more advanced techniques. If we're willing to invest a little bit of time in learning Sigma metrics or Six Sigma benchmarking, we can figure out how to do our Westgard rules, when we need them, and how many of them we need. So you may be familiar with the traditional Westgard rules, but these are the quote-unquote new Westgard rules. This is what we call the Westgard Sigma rules. That is, we take the power of Six Sigma and that benchmarking technique, and we merge it with the Westgard rules. And you can see below the traditional Westgard rules flowchart, you see the Six Sigma, and then the 5 Sigma, and the 4 Sigma, and the 3 Sigma, and that's actually carving up the Westgard rules into different sections. And if you do Six Sigma, then you only have to do one Westgard rule, and we'll discuss how many rules are necessary based on the different Sigma categories. Now, one of the questions we asked as you were registering was, what do you do when there's an out-of-control flag? Do you repeat the control? Do you run a new control? Do you recalibrate? Do you troubleshoot and take corrective action? Your answers were 72% of you repeat the control. This is the conventional approach. You have something that goes out, you run it again. You repeat the control. I like to call that double or nothing QC. You're trying it, you're rolling the dice again to see if the value falls in, and you're hoping that it will, and that way you can move on with your day. And about a quarter of you do something different, which is either you run a new control or you try to recalibrate or perform some maintenance. Now, if we go back just a little bit in the presentation, remember, a lot of you are using 2SD control limits. 2SD control limits cause what? False rejections. How do you respond to a false rejection? If you're constantly hearing these alarms going off, you don't respond to each alarm like it's a true fire. You start to think, do I smell the smoke? Somebody go out in the hall. Do you see any smoke? If not, let's just keep going. So the fact that we may be choosing 2 SD control limits, that corrupts our response to the outliers. And we're tempted to do this repeat QC because we're dealing with so many false alarms. And this matches up pretty close to what we see globally. We see 67% of labs worldwide are repeating the control. 3/4 say they also will troubleshoot and find the root cause. That's, most labs being willing to say, well, we know what we should do is troubleshoot and find the root cause. And then we had an additional 4% say they will repeat the control just as many times as necessary until it falls back in. That is, some labs will repeat not only once, but twice, but 3 times, maybe a dozen times, whatever it takes to get back in. Occasionally, when you put out a survey like this, you get the unvarnished truth. And of course, when we think about all these repeats, that's not saving us money, that's burning money. It's great for your QC vendors, it's great for your manufacturers, your diagnostic manufacturers, because you're burning more product up. You're burning more reagent, you're using more supplies, you're running more controls. That makes everybody but the laboratory more profitable. If you're looking for a way, a low-hanging fruit on saving money, try to figure out how you could reduce the number of times that you're repeating controls and troubleshooting. Again, that will bring us to this Westgard Sigma rules. The Westgard rules themselves, of course, reduce your false rejection rate. But if we use fewer Westgard rules, that means our rejection rate, our false rejection rate goes down even further. I've mentioned Six Sigma. Now, of course, I want to run through just a few of the concepts of Six Sigma and explain how this benchmarking will bring us to lower costs and better QC. Six Sigma is really the goal, and essentially it's a simple way to say we have a process where we've reduced the number of defects to less than 4 out of 1,000,000. So if you want to have fewer than 4 rejected runs out of 1,000,000 reportables, you want Six Sigma. And when General Electric, GE, and Motorola started this Six Sigma movement back in the 90s, they found when they could get their processes to Six Sigma, they had the highest efficiency, they had the happiest customers because obviously they have the most reliable result, and they also achieved their maximum profitability. If you want to talk about some Six Sigma processes in the real world, you think about, well, airline safety. Now, you have to go back before the pandemic. Remember when we used to fly all the time? Well, in the US, less than 3 crashes per 1,000,000 departures. Better than Six Sigma quality. A little bit more mundane, but more relevant to the laboratory. In a European survey of pre-analytical errors, they found the number of samples that were being damaged in transport and the number of samples that were not being stored properly before analysis. Those errors were happening so low that they had achieved Six Sigma. So it's not just that you're looking for Six Sigma in your analytical assay, but even in your pre-analytical processes and post-analytical processes. 5 Sigma is good, but we start to see errors. 233 per 1,000,000 reportables. And this is closer to how many times is a specimen being misidentified, how many requests are being misidentified. Of course, this is assuming you have an electronic system to capture the orders and process the tests. 4 Sigma is where we start to actually experience and we're aware that the process has errors. We're now at above 6,000 defects per 1,000,000 reportables, and this is closer to how often your luggage does not take the same vacation as you. So remember, airlines are very safe, but there is a lost luggage baggage office in every airport, and that's because it happens. It happens often. Another common Four Sigma process is, does the sample come in without enough volume to run all the tests that have been ordered? Does the sample come in and it's hemolyzed? Everybody knows that is a constant problem. It's a Four Sigma process. 3 Sigma is where the theory says that's your minimum acceptable quality. Now we're at 67,000 defects per million, and now we're closer to the contaminated microbiology samples. Again, people know that's a chronic issue, and we have some papers just this year that have noticed the laboratories under the current stress of the pandemic, their pre-analytical error rates are rising. Again, it shouldn't be a real surprise that we put so much stress. We have laboratories operating, all shifts with employees having to do overtime, not for a short period of time, but just for a marathon. That stress creates fractures. We start to see errors go up. And then finally, we have the 1 and 2 Sigma processes. This is what theory tells us is unacceptable. Now we're in the hundreds of thousands of errors. And now we're closer to things like departure delays for the U.S. airline industry. Doesn't matter how safe you are, doesn't matter how well they handle your luggage, sometimes you just don't get to take off. And if you ever had the frustration with your airlines, you know now, well, what is below 3 Sigma feel like? And then, one slight footnote, we know the Theranos trial is beginning, or I should say the trial of Elizabeth Holmes, the former head of Theranos, and what's one reason why her $9 billion evaluated company went to $0 valuation? Because most Theranos assays were below 1 Sigma. So now we understand a little bit about the different positions on this 6 Sigma scale. The next thing we need to do is to put ourselves on that scale. With our tests, where do they fall? Are they 6 Sigma? Are they 3 Sigma? Are they 1 Sigma? The first step in figuring that out is to get a performance specification or a quality requirement. And for those of you in the US, it's pretty simple. You go with the CLIA regulations because the federal government, CMS, is directly regulating how good you need to be. And for non-regulated assays, you go to the proficiency testing providers like CAP or API. They will fill in the goals that aren't directly regulated by CLIA. And outside the US, there's the RCPA for Australians, the RILIBAC for Germans. There's a biologic variation database known as the RICOS goals that's on our website. There's a more updated database hosted by the EFLM. And almost all the resources you see here, we make available on the Westgard website for free. Those tell you how good your tests need to be. In order to understand how good you actually are, so you have a target, are you hitting the target? Well, for that, you need 2 more pieces of information. You need your CV and your bias. And you need to capture this at your most important medical decision level. So you have your CV from your controls, and you have your bias from a number of different possible sources. It could be from your proficiency testing. It could be you're lucky enough to have a reference method or a reference material handy. It could be that you are using a peer comparison software program. That is one program that we encourage because it gives you a lot of data and it's readily at hand. And that allows you to determine your bias once you know your CV and bias. And again, you've been collecting this data all the time. Since the lab opened its doors, you've been collecting CV and bias. So really the only piece of information that may be a little bit new to you is that total allowable error or performance specification. And once you have those 3 items, you can do a sigmametric. And it's a calculation where you take the allowable total error, that's your quality requirement, you subtract the absolute value of the bias, and then you divide by CV. So it's your quality goal minus your inaccuracy divided by your imprecision. And the graph below, the graphic below, is just to give you an idea of how the equation works. Think of that allowable total error as your tolerance limits. That's where you're supposed to keep all your results inside of. You see that true value in the center, that's the clinical truth, that what's really going on with the patient. You want to get that, but if you can keep the result within the allowable total error on either side, you get an answer that may not be perfect, but it's close enough to make the right diagnosis and give the patient the right treatment. When we inject our bias in our CV, however, the bias shifts our distribution away from that true result, and the CV spreads out our distribution of results. So when the bias and the CV are combined, we have a shift, we have a spread, our curve is different, and where that curve goes outside that allowable total error, those are where the defects occur. To make it a little more concrete, let's take a quick example. We have 3 levels of cholesterol QC. This happens to be from a 2014 clinical chemistry study. CLIA directly regulates cholesterol. You have to be good within 10%. So if you're running 3 levels of control, you have CVs at 3 different levels. And if you have a peer group program, or in this case, you had a reference method, it's cholesterol, we know we have a reference network, we can determine our bias at the same 3 levels where we're running our controls to determine CV. And so in this case, we have 3 different possible sigmametrics. At the low end, 10 minus a bias of 3 divided by imprecision of 1, it's better than 6 sigma. In the middle of the range, 10 minus the bias of 2.5 divided by less than 1% imprecision, also better than 6 sigma. At the upper end of the range, 10 minus the bias of 2.3 divided by imprecision of 1, better than 6 sigma at the upper end of the range. Now in this case, we have a really ideal scenario. Every level, every area of the test is above 6 sigma. You might have a different situation. You might find at the low end you have a lower sigma, and the middle of your range, the mid control, has got a higher sigma, and at the upper end you have a much higher sigma. So you'll have different sigmas being measured at different levels of the test. And this can cause some confusion, it might cause some anxiety. What do you do when you see you have different sigmas at different levels? This is why we asked you to collect the data at medically important decision levels. Where's the level that the control is being run that's closest to a decision point that the clinician uses, that makes the most important decision on the patient in terms of diagnosis and treatment? If you can identify that, take the sigma closest to that. The sigma metric closest to the most important decision level, that's how we recommend you judge the test. If you have a very low control, but there aren't any patients there, and you have a low sigma metric, as far as we're concerned, that's not as relevant as a different control level that might be closer to where patients actually are. Once you've made that decision about which sigma metric to pay attention to, that's when you come back to these Westgard sigma rules. And if you're at 6 sigma, you decide the recommendation here is at 6 sigma, you're not using all the Westgard rules. You're just using one rule, 1-3S. And really you're just using 2 control measurements, you're meeting the CLIA minimum. That's all you need to do. And by the way, that is very low, almost no false rejection. If your method is 5 sigma, well, remember that's excellent, but we're going to expand the recommendation to 3 Westgard rules. Now you add the 2-2S, now you add the R4S. You're still just making 2 measurements, it's all done in one run. At 4 sigma, now we need 4 Westgard rules. We have good performance, but we need more control, more rules to properly monitor the method. at 3 sigma, and if you remember, 3 sigma is the minimum acceptable performance, that's when we finally need all the Westgard rules. And we're going to be looking at increasing the number of measurements that we have to make. In the most simple version, we would be saying make 6 measurements instead of 2 or 3. And so you can see with 3 sigma, we need a lot more rules, we need a lot more measurements, and we'll see later, we should probably even run QC more often. This is why the minimum level of performance is not ideal, because it requires much more effort from us. And if it's below 3 sigma, well, the Westgards have run out of rules. And now we would need you, yes, use all the Westgard rules, run as many controls as you can afford, run as frequently as you can afford, but think about other things you could do. Are there non-statistical techniques, average of normals, that you could adopt that would help you in this process? Can you actually improve imprecision or reduce bias? Is this method so poor, maybe you should move it to a different instrument? Maybe you should switch instruments. When you have below 3 sigma quality, when you have Theranos level quality, you need to make some changes. And now let's talk about this QC frequency. I've sort of flirted with it, but I haven't told you any details. QC frequency pretty much is governed by what I would call a planet-based QC frequency. That is, we run it once every revolution of the planet. The planet rotates every 24 hours, thus we run our QC every 24 hours. Is there a relationship to the good of the process to the rotational speed of our planet? Not really. This is just a compliance. We're just meeting regulations. Sometimes there is an increased, maybe 2 or 3 times a day, once every 8 hours. It might match with how often we have different shifts. So, you know, we're not basing it on the planet, now we're basing it on our personnel. And then those of you in the point of care area, you know that there is also this once a month or once a month QC policy called IQCP, and that is literally lunacy. Once per month running QC, that's inadequate, and you might be howling about it. Where we should really focus our QC frequency is around the idea of patient risk, patient-based QC frequency. Patient-based QC frequency, which is also has to be performance-based. That is, we know how good the test needs to be, we know how well our instrument performs, and those two things drive how often we need to run QC. And this brings us back to our registration question. We asked you this as you signed up for this webinar, and we saw that about half of you run QC just once a day, a little under a quarter run it twice a day, and a little lesser than that is running once per shift, which could be 2 or 3 times a day. It really depends on the operational schedule of the laboratory. So again, that's the conventional response, running once a day. When we match that up with the global trends, we see 27%, again, almost a quarter, twice a day. Just a slim majority, similar to your answers, are running once a day, and a little under 20% are running 3 times a day. And thankfully, only 1.6%, and mostly those are point of care users, are lunatics. The data-driven way to QC frequency is to base it on your sigma. So if we have 3 sigma, we should be running our QC every 45 patient samples. And this probably sounds a bit shocking. Those of you who know your patient volumes realize if you had a 3 sigma process, you would have to spend a lot more on controls. You really don't want to do that, so you would prefer to have a process where you had maybe 4 sigma. And now you're running every 200 patient samples. And that, for many Small laboratories starts to match their daily reality. If you're high volume, we really need the 5 sigma tests, because now you can wait until 450 patient samples go by before you need to run QC again. And if you're one of those high-powered, massive core laboratories or reference laboratories, you want 6 sigma, because at 6 sigma you can go 1,000 patient samples before you need to run QC again. So you can see that the sigma really builds up in terms of QC frequency. The better you get, the fewer QC you will have to run. And this brings me to our things that will also force you to run QC maybe more than you needed to mathematically. Even if we find out you could run QC only once per 1,000, but if you only run 300 in a day, and then when the next day starts, the clock starts over and CLIA says you've got to run QC once a day. Another thing that will force you to run QC perhaps more often than your sigma does is your manufacturer's instructions. If your manufacturer says there's a startup procedure, you need to run QC at the beginning of every day or every certain number of X hours, you have to do that, even if the mathematical advice is run it less frequently. Low volume labs, if you have a test where you're only running 100, 150 tests a day, but it's a 6 sigma method, well, you can't space out and say, well, now I only have to run once a week, because your volume shorts out, and then your clock starts again in 24 hours. Another thing you should take into account is what's your realistic ability to recover from a failure. If you could go 1,000, if the math says you could go 1,000 patient samples, but your ability to retest or recall or make corrections to a number of test results is not 1,000, then you're going to have to keep your QC frequency shorter than what the math tells you. Another thing that will come into play is your institutional tolerance for risk. If our recommendations reduce your QC frequency, but your risk management department is not happy with that, you're going to have to go with what your risk managers are telling you. And finally, there's your psychological well-being. Can you sleep at night if we reduce your QC down to once per 1,000? If that's not going to make you, if you're not going to be comfortable with that, we're not going to force you. This is an option. Now, obviously, if you are comfortable with it, if you have the volume that would support being able to go once per 1,000 patient specimens, and you're still meeting all your manufacturer instructions and the CLIA regulations, then running QC at that frequency is probably going to be lower than where you were. And it will give you that opportunity again to save some money and be more efficient. So let's start to wrap up. Why did we call this unconventional QC? Because we want to break conventions. The conventional way, the common wisdom, the most common way of doing QC is you run it for compliance only, you're running the 2 SD control limits, or you're running all the Westgard rules, you're repeating controls, you're going double or nothing, or you're recalibrating, or you're feeling rotten because you have to chase all of these ghosts. And if you're refusing to make these changes, if you're refusing even to consider the idea of changing your QC, please recognize that this is not a sustainable way to run a lab. You have constant pressure to find savings, constant pressure to make the most of your scarce resources, and your scarcest resource is your tech time. You're going to continue to have problems finding staff. There's no infusion of new talent coming on the horizon. So figure out how can you free up more hours for your staff to be able to meet the increasing demands. If you have a lot of staff who are pulling their hair out staring at control charts, that's not a great use of their time. And it's time to become unconventional. The unconventional conclusion I want you to reach: re-examine what you're doing and design your QC. Don't accept some default that was set 10, 20, 30 years ago. Reduce your controls, reduce your rules, reduce your measurements when possible. Choose your QC rules to minimize false rejection and maximize error detection. That's what the Westgard Sigma rules will help you do. So you calculate that analytical Sigma metric, you implement your Westgard Sigma rules. That allows you, again, reduce your rules, reduce your controls, reduce your measurements. Your control costs go down. Your consumption of manufacturer reagent and supplies goes down. Your troubleshooting costs go down. And I leave at the very last recommendation the consideration of changing your QC frequency. I realize for most labs that is a stretch. It's hard to consider. It's a challenge. That's okay. If you can do all the changes in rules and controls and measurements first, that'll get you a great amount of savings. Changing your QC frequency may be something that you postpone until you're in a better place and you're more, you have more of the bandwidth to consider the mathematics and align the recommendations with the realities of your operations. And then lastly, I just want to talk about a program that we offer that gives protocols and training on the application of all these Sigma metrics. We call it the Sigma Metric Verification of Performance Program. We have laboratories all over the world where they have taken training for their staff, they have adapted their QMS, they have benchmarked their quality and then made these changes. You can see more than 75 different examples on the website of labs that have benchmarked their quality on the Sigma scale and the changes they have made. And with that, we reach the end of our formal presentation and we can begin to open up to questions, a live Q&A, and it does look like we have more than a dozen questions, but I do encourage you to keep the questions coming in, because if I don't answer it right now, we will answer all of them and post them on the Westgard website. You'll be able to see your question answered on the website later. So with that, again, I want to thank Technopath and LabRoots for making this event happen. Happy that so many hundreds of you were able to join. I hope you have some questions, and we'll launch right into that now.
Thank you, Sten, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, how do you determine your Six Sigma metric if there is not a total allowable error value mandated by CLIA or CAP, etc.?
All right, that is a great question. Obviously, that comes up. There are tests. Usually the performance specification, that happens after the test has been introduced. So if we have a lot of new tests on the market, it's going to take a while to figure out how good those tests need to be. There's a very rich body of work in the literature about trying to establish performance specifications, and the general framework is start by looking at the clinical use of the test, see how changes in the results will change outcomes or change diagnoses, and then you work that interval back, call that a clinical decision interval, and you're going to work that back into the laboratory to figure out how you, as a laboratory, can keep your error small enough so that you won't change, someone who's sick to someone who's normal, or vice versa. So while there may not be formal specifications, you can always go to your clinicians, go look at the use of the test, and determine it directly yourself. You are empowered to use your professional judgment to set an allowable total error if no one exists anywhere else.
Okay, thank you. Next question. Where do I find the CLIA guidelines you mentioned?
Excellent. So the proficiency testing criteria of CLIA, they're in the Federal Register. So you could type in all those terms I just mentioned on Google, and you eventually will find the list there. On the Westgard website, so Westgard.com, we have a quality requirements section. We list not only the CLIA goals, we list RealiBach, we list RCPA. We have a consolidated table where we try and put a number of different resources from all over the world into one table, so you can see, you can compare the different goals across the global resources. And we even, in our Sigma VP program, we make a recommendation, if there are a dozen different specifications for glucose around the world, which one do we believe is the appropriate one for tests, for laboratories?
Okay, great, thank you. Our next question is, if peer QC data is used to determine bias, what is the ideal set of stats? Are lab cumulative versus peer cumulative? Or are monthly versus peer cumulative? Are monthly, that's the end of the question, I'm sorry. Or are monthly versus peer cumulative?
That is a very good question because it's so well detailed. In a peer group program, you have that monthly set of data, and then you have your cumulative. Now, in general, if you look at all your QC guidelines, if you look at the CLSI C24, which is your recommendations for best practices, they're going to say what you want is 3 to 6 months of cumulative data for your mean and your standard deviation. So ideally, we would like to follow that when we go to Sigmametrics. We want more than 1 month of data. So we would like to do the cumulative comparison, and that might be covering 2 months, it might be covering 6 months, but that long-term performance data, that gives us the best picture of overall how is the method performing. So we have our best picture of bias by doing a comparison of your observed cumulative mean versus the peer cumulative mean.
Okay, thank you. Next question, if different levels on the same analyte have varying sigma levels, is it acceptable to have different rule sets for each level?
That's an important question, and I would say if you decide to do different QC rules on different control levels, that way madness lies. Okay, you will go crazy if you have to look at each level and employ a whole different set of QC rules. So most labs, they choose one QC design for all the levels, whether it's 2 or 3 levels on a test, they all get the same QC design. And I would guess that most software is implemented that way. I haven't seen the granular control of being able to plot your different rules on different levels of a QC test. It might exist, but in my mind, it's better to figure out, let's do one sigmametric for the whole test, and therefore one QC design for the whole test.
Okay, thank you. Next question, when comparing measurement uncertainty, does it have to compare with TAE?
That is, well, let's say, you may have noticed that I did not mention measurement uncertainty in the entirety of my presentation. And for those of you in the US, you may also have noticed that you can operate a laboratory without pretty much ever having to encounter measurement uncertainty. The total allowable error and all of those performance specifications, they were created with the idea of making sigmametrics or QC choices. Total allowable errors were created not for measurement uncertainty. Nevertheless, those total allowable errors, and there are so many resources that are built that way, the proponents of measurement uncertainty have started to borrow the total allowable error limits and use them in some way to compare against your measurement uncertainty. There is what's called a permissible measurement uncertainty, and that is, I am not making this up, that is abbreviated as PU. And your PU, you're not supposed to exceed your PU with your actual measurement uncertainty, or your mu, what I call the mu. The mu should not be bigger than the PU. There are relatively few specifications. The number of PUs out there is very small. They only came out with a few set of PUs this year. So overall, my advice about measurement uncertainty is stay in compliance. If you have to create MU, if you have to mu, do it. But most labs that I have encountered, they calculate their mu, they show it to an inspector, the inspector says great, and then they put that mu away and they never use it. It is something that your ISO 15189 requires, but in practical terms, it's almost never used. Theoretically, it would be great to use with your clinicians to be able to say, this is the result and this is the uncertainty around the result. And then the clinician could make a decision saying, well, the number is here, but it's really in a cloud around there. And I have to be careful. If that cloud looks too big, I shouldn't make any big decisions. Those of you who enjoy reporting results to clinicians, you can guess that a lot of clinicians don't take kindly to being told, here's your number, but it's not really where I told you, it's in this cloud of uncertainty. The clinician often will respond, no, tell me what the number is. And so it's often like a confidence interval. We can report confidence intervals, but usually the clinicians ignore them or find them unhelpful. And that's what you're getting, an unvarnished opinion on measurement uncertainty from a Westgard. And I realize that that might be a contrarian perspective. We have an unconventional perspective on mu.
Okay, thank you. Looks like we have time for one more question. To calculate 6 sigma values, can we use the bias data we obtained with a single sample in the external quality control program, which will be the bias of the previous month's result for all 3 levels of internal quality control until the next inaccuracy data come?
All right, that brings us back to bias. And if we're not using the peer comparison software program, obviously external quality assessment or proficiency testing, it really is designed to determine your bias. Now, that's the positive of it. The negative of proficiency testing is in the US, you might only do it 2 or 3 times a year, and then you might not do that many samples. You may not have that many samples each time you're doing a challenge. So there is a downside, of course, to having fewer data points to determine your bias. But if that's the only way you can determine bias, my opinion is you should go ahead and do that. It's not a great amount of data, but it's your only data on bias. You should go ahead and use it. If you would find more comfort and more, I would say there's more robust stability in a peer group mean versus observed mean determination of bias, I would encourage you to use that.
Okay, great. Thank you. Sten, do you have any final comments for our audience?
Well, again, I want to thank so many hundreds of you who joined us today. It looks like we have more than 50 questions, so while I've been able to answer a handful, we will be answering more, and I encourage you to stay tuned to the Technopath and Westgard website for those following questions. You may have seen my last slide said Sten@Westgard.com. That's my email. Part of my mission is to help you. So please feel free to send more questions to my email address. Also, those answers will be included in an online posting later. I hope that you've come away from this feeling like there are some concrete steps that you can make. There are tools that are free and available for download and use that will help you on this pathway to becoming unconventional, to changing how you do QC, getting better at QC, and having fewer rules and fewer frustrations and fewer controls that you have to run in this process of QC. I hope you have a good rest of your day. I, of course, thank you for all the efforts you are making in fighting this global pandemic. We've never had a moment that made it more clear how important your job is, and the things that you do really save lives. I am really proud. I feel lucky to be able to call laboratory professionals my colleagues.
Well, thank you again, Sten, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Technopath Clinical Diagnostics USA, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period, will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time,